Welcome to Lecture 2.7, Bessel's equation. Bessel's equation is the following ODE, which will arise when we solve the wave equation in polar coordinates. Now, the wave equation is a partial differential equation, so it measures the displacement of a string or a membrane that's vibrating based on position and time. So to solve this, we will separate the variables in position and variables in time. And each of those is going to give us a differential equation. And the one in position is going to give us the following differential equation. So to solve the wave equation in polar coordinates, we have to solve this thing first. So we will do that in this lecture, and then we will use that solution that we derived later in the class. Now, for the wave equation in polar coordinates, this nu here, this is a constant, that's an integer, a positive integer. Nu is Greek for n. Some books have this as n, although in some applications, like the wave equation in spherical coordinates, this nu has to be a half integer. And so you can actually solve this for any constant nu. And so we're just going to leave it like this. And I don't want to call it n either. A, because n can be typically implies an integer, and b, because we will use n for our index in our generalized power series. Okay, so to solve this, notice that that 0 is a regular singular point, because if we divide through by x squared to make this guy monic, then the coefficient of y prime is x divided by x squared. So we are going to assume here that y of x, because this is 0 is a regular singular point, is a generalized power series, which is a n x to the n plus r. And if we take derivatives, y prime of x is n equals 0 to infinity of, n plus r times a n times x to the n plus r minus 1. And y double prime of x is the series n equals 0 to infinity of n plus r of n plus r minus 1 times a n times x to the n plus r minus 2. Okay, so let's plug this back into here. So this first term is x squared y double prime. So that's this last term times x squared. So it's the same thing, except instead of a minus 2, we just omit that. So we have n equals 0 to infinity of n plus r times n plus r minus 1 times a n times x to the n plus r. And then plus xy prime, that's this thing times x, which is the same thing except instead of a minus 1, we just get rid of that. So that is going to be n equals 0 to infinity of n plus r times a n times x to the n plus r. So let me write in blue that's plus xy prime. And then it's always easier to break these two terms into two, because one of them involves, well, different powers of x. We have an x squared here and a constant squared there. So this next one is, well, x squared times y, that's this thing, but instead of an n plus r, we have n plus r plus 2. So let's put in n equals 0 to infinity of a n x to the n plus r plus 2. And then this last one is minus n equals 0 to infinity of a n nu n x to the n plus r, and this whole thing equals 0. So we want to combine these four things into a single sum. Now there's an odd man out, this one with an n plus r plus 2. So we want to shift this index down by 2. Now we could shift the others up by 2, because that's what we've been doing before with our power series and generalized power series. But it's just easier to shift one thing down than three things up. So I'm gonna combine these three terms first, because it's just easier to deal with if we first put them together. And actually, even before that, I'm going to factor out an x to the r, because that appears in every term. So I can write this as x to the r times the sum from 0 to infinity. Now, let's see, what do we have here? Okay, so how many n plus r's do we have? So here's n plus r, and there's an n plus r. So we have n plus r minus 1 of these guys, and then plus 1 of these n plus r's right there. So that it's a minus 1 and a plus 1. So in total we have n plus r, n plus r's. So we have n plus r squared. And then over here we have a minus nu squared. So minus nu squared. And for each of these we have an an and an x to the n plus r, or x to the n because we have our r out here. So an x to the n. And then the next term we have is the sum from n equals 0 to infinity of an x to the n plus r, sorry, not r, n plus 2. I've already taken out the r. Okay, so this thing equals 0. So now we've simplified this a little bit. We just have to combine these two terms. And we could shift up one of these and shift down the other, but it's going to be easier to shift down this one because there's just fewer coefficients. Here we have an n plus r, and if we shift that up, we're going to have a plus 2 in here, and let's just not do that. So to do that, I'm going to let m be equal to this guy. So I'm going to let m be equal to n plus 2, which means that n is equal to m minus 2. And now our index here, n equals 0, that happens when if n equals 0, then m has to be 2. So let me get rid of that. N equals 0 if and only if, precisely when m equals 2. So now let me simplify this. First of all, I can divide through by x to the r. I don't need that. That's never 0, or it's not the 0 function, so I need to set this guy equal to 0. So I get n equals 0 up to infinity of n plus r. So I'm just going to copy and paste this first term. I'm not going to change it at all. an x to the n. Now this term, this next one, I'm going to start from, now I could call all these things m, right? So this is m, from m equals 2 to infinity of m minus 2 times x to the m. But then I could just change the m back to n. So I'm going to skip that step and I'm going to just call it n. So we're going from n equals 2 to infinity times a to the n minus 2 times x to the n, and this is equal to 0. Now I can add these things together. So let's do that. Well, hold on. Let's be careful. What's the problem here? We have this n equals 2 term here. We have an n equals 0 term here. So if we want to add these things together, we have to pick off the first two terms here. Remember we did that last time? If I want to refresh your memory, so if this is n equals 0 to infinity of, let's say, x to the n, I don't want to say 0 to infinity, let me say 4, plus n equals 2 to infinity of y to the n. Let's say 4. I don't know why I'm saying infinity. Let's make those 4. Well, this is equal to 1 plus x squared plus x cubed plus x to the 4th. And this y one starts at 2, so it's plus y squared plus y cubed plus y to the 4th. And if we add these things up, we have to just pick off these by themselves and say that's 1 plus x, but then we can add these together, n equals 2 to 4. I finally remembered that part, x to the n plus y to the n. Okay, so the moral is we have to pick off these first two terms. So let's do that. So this is equal to, so the n equals 0 term, let's do that first. So the n equals 0 term, it's r squared minus nu squared. So it's r squared minus nu squared times a naught times x to the 0. So it's just 1. So this is when, I'm going to say this is when n equals 0. Now let's do the a1 term. So let's say, so when the n equals 1 term. So when n equals 1, this is r plus 1. So now we have r plus 1 quantity squared minus nu squared times a1 times x. This is the n equals 1 term. And now we can add together what's remaining of these two sums and write plus n equals 2 to infinity of, let's see, so we have this, well, let's just combine them and see what happens. So we have n plus r squared minus nu squared times let's see, where were we? A n and then plus a n minus 2 times x to the n. And this whole thing equals 0. So I think I can do this here. Okay, so now we have to set this guy equal to 0. Oh, and what else? Well, this whole thing is equal to the 0 function. So not only do we have to set this coefficient to 0, but this thing has to be, so each of these has to be equal to 0 as well. Each of these coefficients has to be 0. So let's see what we can say. So let's start with the first one. Well, a naught might be 0, might not be 0. But without loss of generality, if we have a generalized power series like this, that is going to have a lowest non-zero term, right? And let's just call a naught that lowest non-zero term. Because if this happened to be 0 and a1 were non-zero, we could just re-Christian that and just declare that to be a naught. So let's just assume that a naught is non-zero. So I'm going to add that up here. A naught is not equal to 0. We can't always do this with a power series, but because we have this mysterious x to the r outside, even if the n equals first term is the lowest non-zero term, we could just bump up r by 1. So we're assuming that a naught is non-zero. So we can declare a naught to be the lowest non-zero coefficient. And again, we don't have to worry about this being the constant term, because if it were the n equals 4 term, we could just bump up r by 4. So since a naught is non-zero, that means that that tells us right away that r squared minus nu squared is equal to 0. And this thing factors as r plus nu times r minus nu. So this tells us right away that r equals plus or minus nu. So these are the only possible values for r. R has to be plus or minus nu if there is a solution of this form. So we're assuming there's a generalized power series solution, and we have just determined that r has to be plus or minus nu. Okay, next term, this x term. So this coefficient has to be equal to 0. We've just said that r has to be plus or minus nu. So in that case, there's no way that r plus 1 squared minus nu squared is equal to 0. Because r is not equal to, or r plus 1 squared is not equal to nu squared. R squared is equal to nu squared. So this thing is not equal to 0. Definitely not. So that tells us that a1 has to be equal to 0. So that tells us that a1 has to be equal to 0. So for whatever the smallest non-zero coefficient is, the next one has to be equal to 0. And this last one, that gives us the recurrence relation. This is going to tell us that if we set that equal to 0, an has to be negative 1 times n plus r quantity squared minus nu squared times an minus 2. So that is our recurrence relation. And so this tells us an in terms of an minus 2. So in particular, if a1 is equal to 0, then a3 is some constant times 0, has to also be equal to 0. So this tells us right away that a3 and a5 and all of the odd terms are equal to 0. So now we have determined what r has to be. We've determined that all of the odd terms have to be 0, and we have a recurrence relation for the nth term in terms of the n minus second term. Let's summarize where we've gotten so far. We want to solve Bessel's equation. This is a second order ODE, and 0 is a regular singular point. So we assume that there is a generalized power series solution. We're guaranteed to have one of those, and that's just an ordinary power series times x to the r. And r might be an integer, it might be negative, it might be a fraction or something else. So we take this, we take its derivatives, and we plug it into the ODE, and we combine that into a single, well, we have to shift the term, but then we combine everything into a single power series. But we had to pull off two terms in the process, pick them off. So we can always assume that this generalized power series, if it's non-zero, then it's going to have some smallest non-zero term. And whatever the coefficient of x is in that term, that is r, and a naught is non-zero because we're taking the smallest non-zero term. So we can always assume that a naught is non-zero. If we do that, that means that r squared minus nu squared is equal to 0. So r equals plus or minus nu. Now if r is plus or minus nu, then r plus 1 is not equal to nu squared. So that means that this thing is not 0. And that means that a1 has to be 0. So now we get that a1 has to be 0. And finally we get this recurrence, which says that an equals negative 1 over n plus r quantity squared minus nu squared times an minus 2. And, well, we're going to do these two things separately. R is plus or minus nu. We're actually only going to do plus nu, now that I think of it, because it's not at all obvious. But these two power series solutions for plus nu and minus nu are actually literally dependent. Not at all obvious, but I will make that argument later. Okay, so this is the recurrence for an. And so if r equals nu, let's write out what this simplifies to. So let's see. See if we can do this without writing down too much. So in the bottom of the fraction, we have n squared. Heck, let's just do it to be, so we don't miss anything. So negative 1 on top, an minus 2 here, and in the bottom we have an n squared plus 2 nr, and r is equal to nu, plus nu squared minus nu squared. So we get some cancellation here. And so what we get is we get that an equals negative 1 over 2n nu plus n squared, an minus 2. So this is going to be our recurrence relation. Let's compute a few terms for this. So a naught is non-zero. So a naught could be anything. We can literally pick a naught to be anything, and we get a generalized power series solution for this. So let's pick a nice convenient term for a naught, so everything else, or so we get a nice formula for an. Now in the past when we've done this, we've just set a naught to be 1, right? And that makes things easier. I'm going to pull a trick up my sleeve and do something differently. I'm going to set a naught. This is not something you would ever come up with on your own, but this is the sort of thing that when you play around with this for days in a row and you tweak the formulas, you realize this thing works out nicer. So I'm going to say, let's let a naught be 2 to the nu times nu factorial. Not at all clear why we're doing that, but bear with me. So let's compute a few of the a few of the smallest terms. So when n equals 2, we have that a2 is equal to, let's use this formula, we get 1 over 4 nu plus 4. So we get negative 1 over 4 nu plus 4 times a naught. And now I'm going to plug a naught in for, or I'm going to plug that formula in for a naught. And let's see what we get. We get minus, let's be careful here, it's easy to make a mistake, 1 over 4 times nu plus 1 times 1 over 2 to the nu times nu factorial. And then I'm going to write this as negative 1 out in front. And then there's going to be I'm going to put a 1/2 here. How many 1/2s do we have? Well, we have, see, we have a 1/2 squared right here. That's the 1/4. But we also have a 1/2 to the nu right there. So I'm going to write this as a 1/2 plus nu plus 2. And then what do we have left over? We have a fraction. We have 1 over, let's see, we have a nu factorial here and a nu plus 1. So together, that's going to be nu plus 1 factorial. Now let me say something. I've been saying, so here I've said factorial, and that kind of implies that nu is an integer. And I haven't actually explicitly said that here. I've said r is plus or minus nu. Now in Bessel's equation, I guess I've sort of said that. For Bessel's equation in polar coordinates, this is going to end up being an integer. But in other applications like spherical coordinates, this ends up being things like a half integer. But fortunately, you may or may not have heard of this, there is something called the gamma function, which is an analytic, what's it called? Analytic continuation of the factorial. There's a way to define the factorial function, not just for the integers, but for all positive numbers. But that's not something we have to worry about here. For now, just assume that nu is indeed an integer. So we do that, we get this nice formula for a2. Now I'm going to make it even more complicated. I'm going to put a 1 factorial here, just because I have a little bit of foresight as to what's going to come. Because I have notes, I know what's coming next. It's not something you would do on your own. But let's see what happens when we get n equals 4. So when n equals 4, now we have a4 equals negative 1 over 8 nu plus 16 times a2. That's just this box formula right here. And now, what is that? That is, let's see, so we got to put this guy in for a2. So if we do that, we get, let's see, what do we get? So first of all, we get a positive 1, and then let's factor out the 8. So we get 1 over 8 times nu plus 2. And then what comes next? So we have a 1/2 times a nu plus 2. And then we have this, let's just stick everything else right here, 1 factorial times nu plus 1 factorial. And now let's see how to simplify this. So this is negative 1 squared. So I know that's a plus, but I'm going to write that so you can see the pattern. Negative 1 squared times 1/2. Now we have a nu plus 2, but we also have a 1/8 here. So I'm going to write that, well, that's nu plus, so this is 1/2 to the cubed, so that's nu plus 5. I'm actually only going to write 1/2 times nu plus 4. I know my nu's look like gammas sometimes. I'm sorry about that. These are all nu's. Because I'm going to stick the other copy of 2 right down here. And I'm going to write this as 2 factorial times nu plus 2 factorial times 1. So this is our formula for A4, I'm sorry. And it's not hard to see that the pattern continues. So A2m, turns out it's negative 1 to the m, so it's an alternating series. And then it's going to be 1/2 to the nu plus 2m. And then we have let's make that a better m. And then we have 1 over m factorial times nu plus m factorial. So that's the general formula. So we have a function, y of x. I'm going to call it j nu of x. So I'm going to plug it back into here right now. So j nu of x, this is our solution for when r equals nu. That is going to be the infinite sum from m equals 0 to infinity of negative 1 to the m times 1 over m factorial, nu plus m factorial, and x over 2 to the 2m plus nu. So this is called the Bessel function of order or degree nu. Now this only works for nu being an integer, but as I said earlier, there's a nice way to extend this to non-integers using this so-called gamma function, which really is like the factorial function, but it is defined for all positive numbers. Won't get into that. It's not that outside of the scope of the class for this lecture, but this is one solution. Now we could do the same thing for r equals negative nu. Well, almost. We have a problem because you don't have this factorial business defined for negative numbers. But there is a way to get around that. But if you do get around that, it's not at all obvious, but it does not actually give you another solution. It gives you a scalar multiple of the original solution. Again, not at all clear, but I will hopefully convince you of that on the next slide. Yeah, so this is one solution, and any scalar multiple of this is a solution. And let me show you what these things look like on the next slide, if you graph them. So here is that function again, j nu of x. This is called a Bessel function of the first kind, and there's one of these for each nu. So it's called the nth Bessel. That sounds weird. If it's an integer n, we call it the nth Bessel function of the first kind. So here's that generalized power series again. And let me just write down what the 0th one is. So for nu equals 0, we get a generalized power series, which is negative 1 to the m. And then we have an m factorial and another m factorial here. So we have m factorial squared. And then we have x over 2 to the 2m. So x over 2 to the 2m. And if you plot these things, this is what they look like. Again, it's not fun to just plot this thing, so as a series, but most computer packages like Maple or Mathematica, Wolfram Alpha, all have built-in Bessel functions because they are so common. So again, here's what they look like. There's no really closed form solution other than this infinite sum. Let's once again step back and summarize what we've done. Look at the big picture. So we solved Bessel's equation, this ODE, using the Frobenius method, and we found two generalized power series solutions. Now, nu is a constant. It's often an integer for many applications, but not always. So we have two generalized power series solutions. First one is an ordinary power series times x to the r, where r is nu, so times x to the nu. And the second one is times x to the negative nu. Unfortunately, if nu is an integer, then these are not linearly independent solutions. Now, that is not at all obvious, and I think I lied earlier when I said I would convince you why this is the case, because I don't really have a good explanation for why it is myself. I mean, I'm sure it can be verified in a very technical and roundabout fashion. That's well beyond the scope of this class. But what I want you to take away from this is exactly what I have taken away from it, which is if nu is an integer, these are not linearly independent. Now, if nu is an integer, this is called j nu of x, integer or not, it's called that, and this is j negative nu of x, then these are linearly independent, and your general solution is therefore c1 j nu of x plus c2 j negative nu of x, and you're done. But that's often not the case. Now, if nu is an integer, and let's assume it's an integer for the rest of this slide, because otherwise we have our general solution and we're done, then we can find the second solution by computing the Wronskian. Remember that from a few lectures ago? So the Wronskian, to refresh your memory, let's take this ODE and let's make the y double prime term monic. So we have y double prime plus 1 over x y prime plus x squared minus nu squared over x squared y equals 0. And this term is a of x, and this, remember, is b of x. So the Wronskian is e to the integral, negative integral of a of x. In this case, that's e to the negative integral of 1 over x, which is e to the negative natural log of x plus c. And you can put the c in front, and this is c e to the natural log of x, and negative 1 up top. And of course, this in the parentheses is just equal to x. So this is c x to the negative 1, or just c over x. So that's the Wronskian. And first common is, since that is c over x, this is unbounded as x goes to 0. So both of these solutions, y1 and whatever our second one is, cannot be bounded at the origin, because this first one is bounded. So whatever our second solution is, it's going to have to go off to infinity, or negative infinity, as we get to the origin. Okay, so what else? So remember that there's this technique called reduction of order, where we can actually find the second solution from the first one in the Wronskian. So what you do is, using Abel's theorem, you get this first order ODE that in theory you can solve, and not surprisingly, that's going to be super messy. It's going to involve a Bessel function and this c over x, and it can be done. If you look online, you can find a few places where there are, I don't know, 8 or 10 lines of math, but they skip some major steps. And then there's other books that show every gory detail, and even they say, we will not carry out all of the complications because it is really messy. But you can use this reduction of order technique to get the second solution. Before we say more about that, this first solution, as I said, has a name. It's called a Bessel function of the first kind, and for each fixed nu, this is the formula that we derived. Now this holds whether nu is integer or not an integer. And the second solution, as we said, we can find it using the Wronskian and the reduction of order, but we can also use variation of parameters. So remember that technique? So you assume that the second solution is the first solution, y1, this guy, times v of x, and you plug this in and solve for v of x. Now, mathematically, this is just about as messy as a reduction of order technique. They boil down to the same math that you have to do. We're not going to do either of them. But once you do this and you properly normalize the solution, then you get a function denoted with a capital Y, so y nu of x, called a Bessel function of the second kind. And that satisfies an even crazier relation. So there's no nice formula for this, like there's no nice formula for the Bessel function of the first kind for the j's, but this one is even messier. And there's a bunch of different ways you can write it. If you Google it, you'll see a whole bunch of different ways to write these y's. The simplest one is probably in terms of the regular Bessel functions. So it's this formula, j alpha of x cosine of alpha pi minus j negative alpha of x divided by sine of alpha pi. And, well, if nu is a non-integer, you can plug this in and everything is defined, and that's how y nu is defined. If nu is an integer, then you'd be dividing by 0. So you can't do that, so you have to take a limit. And this limit does exist, also non-trivial. But this is This is the Bessel function of the second kind. This is a very common function. Both of these guys, you don't really want to write out by hand, but they are so common that any mathematical software package like Wolfram Alpha, MATLAB, Mathematica, Maple, all of those are going to have these functions built in. Here's what the Bessel functions of the second kind look like if you plot them. So again, here are the formulas. They are defined in terms of the Bessel functions of the first kind, which are given by this formula. Now, these things are all unbounded at 0. They go off to negative infinity. So one reason why these are less common, or why the y's are less common than the j's, is because the biggest physical application of the Bessel functions are they are solutions to the wave equation in polar coordinates. So picture a circular drum, something like this. You got drumsticks, and when you hit this, there are waves that. So the surface of the drum has waves going back and forth, but subject to the fact that the boundary of the drum does not move. So if you want to model the waves in this drum, these things are Bessel functions, or they are a superposition of Bessel functions. But they're clearly not Bessel functions of the second kind because these go off to negative infinity. So because of this natural boundary condition of the drum, the Bessel functions that come up in practice in this physical application are just the ones of the first kind.